Hello everyone, thank you very much for joining me again. Today we continue our discussions in the playlist of data structures and algorithms with trees. As our example, we will take a binary tree, a binary search tree you will see immediately, which is one of the simplest implementations, tree implementations. Of course, there are many more, which we will discuss in the next lessons, but we have to start with something, no? And I hope you will enjoy also this discussion. If you are watching the event live, remember you can use the live chat there. You know that I'm always keeping one of my eyes on the live chat. And if you are watching the event recorded, remember you have the comment section, and you know that I'm trying my best to answer all the comments and questions. So with that being said, let's start our discussion. I'm gonna share my screen, and as you know, I'm gonna start first of all describing the theory behind trees. So I want to cover all the gaps in case there are gaps there, and then we're gonna jump into my IntelliJ here. And we're gonna work on a simplistic implementation of a binary search tree, because implementing the stuff is one of the most important pieces of really knowing what's there, no? So we need to figure out the theory, but we need to apply it as well, and you know that's my philosophy. With that being said, so let me talk about what trees are. So trees are data structures where elements contain values and they have links among them such that there are no cycles. So what does that mean? Because it might sound confusing. It means that you have these elements that we usually call nodes. The elements usually define something. They can have values. So in the most simplistic representation, we have one value per each node, and to make it simple, very simple, let's say that this value is a very simple integer, so only a number. Okay, it can be anything there, so you can even have a trees of trees, but let's start with the beginning and understand the stuff there. So a tree is where you have these elements that we call nodes, and the nodes have links between them, okay, in such a way in which there are no cycles. So this 4 here might, for example, link to the 3/8 below, and for example one of these can link to another one, and then you can have as many as you'd like, both on the horizontal and on the vertical. And having cycles would actually mean, like, for example, if you would have had this situation here, this would be a cycle, no? So in such a case, this is not a tree anymore, it's a graph. And we will discuss about graphs somewhere in the future. But since we discussed tree nows, we know there should be no such cycle. So a tree is a tree if there are links between the nodes in such a way in which there are no cycles. This being said, it's called a tree because it starts with this element, this unique element that is called a root, and then it actually, you can put it in such a way in which it looks like a reverse tree. Usually we start from the root and we put all the elements down below. So it looks like this is the root of the tree and this is the tree, which can be as large as you want. And that's why we call this a tree. You can say that a tree is a more particular kind of graph, but since we didn't discuss graphs and we will discuss them somewhere in the future, I will not jump now into that. I want you to focus only on this structure and remember a few notions. So remember, these all are called nodes. The nodes usually have values, so they have to represent something, and in the most simplistic representation we have, let's say in our case, some numbers. the nodes have links between them. So these edges, basically how we call them, are the links between the nodes. And if you put it like this, now you have a tree. Okay. Now, and also this is called the root. Okay, so very important. The first node where the tree starts is the root. Now, besides this, there are many kinds of trees. Now, I have just draw here a random simplistic representation of a tree, just to make you aware of what a tree is. Depending on how you design the trees, you split them in different categories. And I think there are like, I'm not even sure, 12, 13, 14 kinds of categories out there in which you can split all the possible trees. You have prefix trees, binary search trees, suffix trees, Merkle trees, heaps. You know heaps, probably you've heard the term of a heap. We will also discuss it in the future. It's also a tree representation, no? So trees are very important. There are many things you can do with trees. You can do by representing data as trees. So they are part of many algorithms and data processing. So that's why it's important to understand trees as data structures, because they are usable in many cases. Now let's dissect one of the cases today, which we will also implement. We will not take a random tree. We will take a specific kind of tree that we call a binary search tree. Why is it called a binary search tree? Well, this tree has a rule, and the rule is you can only have two children per each other node. So for example, my number 4 here can only have, let's actually make it a little bit bigger, no, just to have room for my example. Number 9 here can only have one node on the left and one node on the right. That's why it's binary, because it's only 2 children per node. If you refer to a tree as a data structure, there is no limitation. But if your tree needs to be a binary tree, then you have this limitation, 2 children per parent. And if you want to design a binary search tree, then it has one more rule. Everything that's on the left is smaller than the parent. Everything that's on the right is bigger than the parent. So I will show you why this is helpful. So for example, here I can have a 5, and here I can have a 12. On the right side it must be bigger, on the left side it must be smaller. Let's also draw the links, so the edges between the nodes. And whenever you add anything to this tree, you have to figure out where it belongs. So if I want to add any specific number, like 7 for example, you have to figure out, is 7 bigger or smaller than 9? Then you start with the root, of course. So yeah, definitely 7 is smaller than 9. So if it's smaller, you go on the left side. Then you actually do this thing again and again with all the nodes that you encounter. So you do the same with 5. Is 7 smaller or bigger than 5? Well, it is bigger. In this case, it should go on the right side. But since there is no right side, if this was the add operation, then you create a right side of this node. So now you have the 7 on the right side of the 5 here. If that was a search operation, you would have just said, hey, 7 doesn't exist. So it's a binary search tree. First of all, it's a binary tree because you only have 2 children per parent. And secondly, it's a binary search tree because it has this rule that helps you easily search throughout the group of values. Remember, we have discussed that searching is one of the most encountered operations in data structures, and we have even learned that with hash sets something similar happens. Now, in the previous lesson we discussed, where we discussed hash sets, you've learned that whenever adding some value to a hash set, it is processed and it is added such in a way in which it facilitates later the retrieval. So you can easily find if a value exists or not based on how they are grouped. And I was making that analogy with the playing cards and the way you group the playing cards to make sure that you easily find any card. These kinds of data structures are made on the philosophy of investing more in arranging first in a specific way the values, such that then other operations will be easier. So this is the philosophy on which the binary search tree also works. Now you invest more when adding the value in the group, such that then later you will have other operations that will be easier to do, like finding, for example, in a large amount of values a specific element. And then you can, whenever you do such an you make such an operation, now you take the same approach. So let's say you want to add value 3. If you want to add value 3, you go here, you compare it with 9, it's smaller than 9, so you go on the left side, it's smaller than 5, then you have to go on the right side, on the left side, there is no node on the left side, then this is the place. So when we have encountered the null, then this is the place where you want to add the value. And again, you can do this exercise multiple times just to make sure that you understand how this works. So for example, if you want to add an 8 now, the 8 is smaller than 9, so you go here, but is bigger than 5, so you go here, and is bigger than 7, so that means you will add this on the right hand side of the 7. And this is how you build the binary search tree. So this is the process of building a binary search tree, and every time you now have to search for a value is very easy, because using the same rule you can create the exact path for finding a value. So for example, if you want to find value 8 now, you will just follow, this is 9, 8 is smaller, so you go here, you didn't find it yet, but it's bigger than what's here, you go here, and then you go here, you found the 8. If it's something that doesn't exist, for example, any number that 6, for example, so if you go here, you can say, hey, this is a 9, 6 should be smaller, you go here, this is a 5, 6 should be bigger, you go here, 6 should be smaller, and then suddenly you see there is nothing smaller than 7, it's a null, which means that value 6 doesn't exist in the group. So you see, I only had to go through a short path to find out that this 6 doesn't exist, and also a very short path allows me to find an element that exists in the tree. So this is the philosophy. Now, how do we build it? Let's go to an IntelliJ. So since we have Java 21 now, I changed to the new philosophy of using the new main method, even though, yeah, I know it doesn't make any difference, but let's use it. And I'm gonna build my binary search tree here. So what I need is a class that defines the node. And of course, I will make it very simple. So I'm just considering a value of a type integer, but remember, you can have a generic type. Normally, if you would build this as a collection yourself, you would need generic types. And then what does any node have in a binary search tree? It has to have the left-hand side and the right-hand side. So node left and right should be here. And then I would actually add also a constructor for at least the value whenever you create a node. So that's the minimum node that you have, which represents very well the drawing we made earlier. So now, whenever you have any tree, it should have at least a root node. Initially, the tree is empty, doesn't have the root node. But whenever you create it, what you can actually do, usually you don't necessarily have to have here the node, you have the value, and then you create the node for that specific value, and this is the root. No, this is how you add the root, or you can simply start by having an empty root. Why not? This can be the case as well. So it's your choice if you want to start with a root or not. So you can have actually the default constructor as well, which gives you the opportunity to start with an empty tree. So that means that when you create the tree, it will be something like var tree new binary search tree, and you can either give a first value here or start from nothing. Let's discuss about and try to implement at least the adding and the parsing, now if you want, of the trees. So let's find out how we how can we implement the adding a value and maybe retrieving a value, or parsing all the values in order. The binary search tree basically helps us to work with these values very efficiently. No, that's one of its purposes, and that's why we are using it, as you will see. So what if I want to have a method that's called add, and this adds an integer value to my tree? So that should be something like tree add, and then you should be able to add multiple values here. Okay. So if you want to do that, the easiest way to implement the adding would be to use a recursive method. Why? Why it's a recursive method the easiest way? Because if you take a look again on the diagram, you will have to repeat the same operation for each and every node. So if I want to add one more value, say I want to add value 2, then I start with the root, and then for each node until I find the null, I will have to repeat the same set of operations, which is the value smaller or bigger than the current node? If it's smaller, you go on the left side. If it's bigger, you go on the right side, and then you do the same thing until you find the null. And the easiest is simply define the operations in a method and then call it within itself, basically allowing the method through recursiveness to go throughout the whole tree, from the root to wherever the value needs to be added. So that means here, what I will do is I will create an add method that gets the current node and the value you would like to add, and I will make sure that this calls within itself. So it has to call itself such in a way in which if you have reached the value null, so if the current node is null, then it means you have reached the place where you create the tree. So in that case, you return a new node for that specific value. So this will be the place where the recursive nest ends. Whenever a null is reached, it means you cannot go beyond. It means you've reached the place where you have to add that value. But if that's not the case, then you have to figure out on which part you have to go next. So that will be if the current value is smaller than the value of the node, then you are going on the left side. Else, you are going on the right side, and then at the very end you return the node. So you return the current node, which we will use throughout here up to the root, where we call this method for the root and the value. No, so we start from the root and try to figure out where can we add the value. So if the value is smaller, we go on the left. So current left is the same method add for the left and the value. Sorry, it's current. I think it's current, not current left. No. And if it's bigger, you go on the right side. So what you say, going back here, I start with the empty tree. So let's say I start with the empty tree. No. So this doesn't exist now, which means the root is null. What happens when you call this with the root being null? So the add will enter directly on this if and will return a new node with the specific value, say 9, and will assign that to the root. So that's basically what happens for the first iteration. So I have created at the first execution, I'm going to take exactly this value, the 4. No, I'm going to add the 4 here as being my first execution. And now what happens when the method is called again with an 8? So if it's called again with an 8, it's the same. Now it starts with the root. So root is the 4. It is not null. No. So it will not enter this condition anymore. But then we say 8 is smaller than 4. So it enters on this value actually. And it actually creates, it calls again the same method for the right with the 8 value, creating basically the current node. I think it's current, actually current left and right here, no? To make sense. So I start with the current, and then I'm on the else side, I'm on the right, and here it goes again. And when it goes again, this is basically null, and it creates a new node and it returns it. It returns the new node, no, here, with the 8, making actually the 8 to be on the right side of this root, which is good because 8 is bigger than 4. Something like that. And then if I'm gonna do the same thing again with the 1, so it starts again with the root value. The root value is number 4. It's not null, so it goes further. 1 is smaller, so it goes on the left. And then it calls again the method, and the left is null, which means it will enter here, creating the node for value 1, which basically will put the value 1 on the left side. Come on. Okay, I seem not to be able to convince my Inkscape here to work. Okay, so this is value 1, no? So value 1, it's on the left side. and so on and so forth. So it should basically work the same regardless of how deep you go in the tree. Now we can actually try to use the debugger to see that it works indeed as I desire. So what I'm gonna do here is I'm gonna add a breakpoint on the add, and I will try to see if indeed it works as I expect it to work. So I'm gonna start this with the debugger. Okay, so it's value 4, which is the first here, is the first time the add method is called. So I'm going, and the root doesn't exist, it's null. So it means that the value 4, for value 4, a new node will be created. So I'm gonna step into, and you see it creates the node and it returns it. And now this becomes the root. And everything ends. And then I'm gonna jump, and this is the next operation where we have an 8, but this time the root is not null. No, the root is my value 4. The left and the right, however, they are nulls. So when I'm gonna go on the next line here, it will skip over this. This is false because the current, which is root, is not null. And it will go into my condition, going from the if into the else. Why? Because the condition is false. 8 is smaller than, 8 is bigger than the root's value, so it should go on the right side of the tree. So what happens now is that we will step again into, because we will now call with the null value, which will become the right side here. So I'm now again in the same method, but now the current node is null because it's the right of 4, which doesn't exist yet. But we are going to build it. So we return it. It automatically becomes now the right side of the root. So the current here, where we came back, is the root. And its right side, to its right side will be assigned the 8. And then everything ends again. And this will repeat now for the 1, and then it will repeat also for the 12. Forming in the end, and I think we can see it, and we're gonna be back. I missed it. I would have expected it goes back here. We could have seen the entire tree. So I hope this makes clear how the addition works. Now, what if we want to parse this tree? So now if you want to search for a value, if you want the contains will actually work the same way. It's just that instead of trying to find the null to add the value, for contains it's even easier, because when you find the null, you just quit everything, meaning you haven't found the value, so you don't have an equals anymore. In that case, you simply just return a false or a null, or depending on how you want to create your operation. Or if you want, you parse it and you find the value, then you simply return the value. So adding and contains are two very similar operations, because they both do the same thing. They follow the path depending on the side based on the rule of the binary search tree. And you either find the value, case in which searching stops and the value is returned, or you return true or false, maybe, depending on what you want to build your app. Or you didn't find it, case in which you will get into a null. Whenever you found a null, then it means you didn't find the value, so you return null, or you return false, or whatever you want your code to look like. If we want to parse the values, so I think we can actually have something like parse the tree. So we should also use a recurrence here. Which would be parse of a specific node, because you parse a specific node. And then I think if you reach null, you return, no? And this should be the stop condition. Otherwise, you should parse the right. Sorry, the left first, I guess. You should parse the left. You should display the value of the current. And then you should parse again the right. So you take the tree and you parse both the left and the right, no? Something like that. And then here, of course, we parse starting with the root, considering we have a root. So normally I should be able to say here tree parse, which means follow all the values in the tree by going to the left and to the right of every node. So you can see what happened here. You added the values, counting that we take first the lefts and then the rights, the values will be in the ascending order. So imagine what happened here in our case: 4, 1, 8, and 12. Let me add the 12 as well, which would be somewhere on the right here. So you saw what happened. I started with the root and then I said parse the left. So I went with the parse on the 1, and then I said parse the left as well, but 1 doesn't have anything on the left. So it came back, it returned and it came back, it displayed 1, and then it tried to parse the right of the 1, but 1 doesn't have any right side. So it came back and the method ended. So it returned to 4. It displayed 4 and then it started printing the right side of 4. And then when printing the right side of 4, it started with the 8. And since 8 doesn't have a left side, it printed 8. And then it continued on with the right side, where I again don't have a left side. I print 12, and then I don't have a right side, and everything returns and everything stops. So if you want to see that also with the debugger, which I recommend you, is you go here and let's see what happens. Okay, so I'm starting parsing. Obviously, I'm on the root, so it is not null, it's the 4 here. 4 is my root. And then what will happen is that it will try to parse first the left side of the root, then the right side of the root. So now it will go here and it will call again the same function, but for the left side of the root, which is 1. Okay, so when I'm now going back, I'm again on the first line of the parse, but the current node is number 1. Since 1 is also not null, it will try to go again and parse its left side first. So I'm again on the first line, but this time is for the left side of 1. since there is no left side of 1, as you can see also from my drawing, 1 doesn't have any children, not on the left and nor on the right. The current node, which is the left side of 1, it's null. The condition obviously is true, which means that the method doesn't go further, it simply returns because there is no longer anything to parse. When it returns to the call which was made for 1. And what we do in that case, we print the value of the current node, which is 1. And then we continue with parsing the right side of 1. Since obviously there is no right side of 1, the same thing will happen. We call the method with null, which ends up in returning without doing anything because there is nothing to parse. Now that we have parsed both the left side and the right side of 1, it's time to return to the previous call, which remained here for value 4. It then goes, prints the value 4, which is the root, and goes on the right side of 4, which is node with value 8. So it enters again the method, but with 8, for which it tries to parse the left side. 8 doesn't have a left side, so left is null. So when it will enter for that, it will return again, and then goes into printing 8, and further goes into parsing the right side. Right side, which is value 12. And regardless on how long the tree is, it will always follow the same algorithm, meaning it will always start with the root and then go on the left and try to print the whole left before printing the values for each node and then going for the right. So the question is the first element that we are adding is root node in this example? Yes, basically always the first element that you add to the tree, it will become the root, because in the at least in the binary search tree, yeah, you don't generalize this for all the kinds of trees, but the binary search tree, whenever you add an element, it will become the root, and then whenever you add something, it will fall on one of the directions, or either on the left side or on the right side of the root. If you are adding a smaller element than the root, it will end up on the left side of the root. If you are adding one that is larger, it will end up on the right side of the root. If you try to add the same element twice, it will not work because, well, if you go back to our algorithm for adding, you will see here that, where is it? Here it is. You will see here that I don't have anything happening for equal. So I either have something happening for less or for more. Actually, I think this is a glitch in my algorithm, no? Normally, and good that I thought about that, I should have actually added one more if here. I should have also said if value is larger, because otherwise for equals it would go on the same, and then you would be able to add duplicates to the tree, which is normally not something you want. But now if I added this condition, now the equal case is avoided completely. Since I don't have any equal, it will always fall on returning the current node without adding anything to it. So in such a case, and this is the correct way of implementing it, adding this as well, in such a case, you cannot have duplicated values in the trees, which is again normal for a binary search tree. So you see, now this is the simplest implementation of a binary search tree. It's a non-balanced binary search tree. I will discuss balanced binary search trees and balanced trees in a later version, in a later lesson. But I wanted to start with the simplest tree, and the simplest algorithm, I believe this is the simplest algorithm, or at least it looks simple enough from my point of view, that you can do with a tree. And to make you understand what a tree is and which is a use case for which you would implement a tree, and in the end this is also the foundation of the red black leaves tree, which is what's behind the scenes of the TreeSet implementation and the TreeMap implementation, which are known implementations of the Java collections framework in the JDK. Yeah, it will help you like later understand how those work as well. So if we now look into comparing this to what Java offers us, like again the TreeSet, for example, this is not exactly what the TreeSet is behind the scenes, because behind the scenes of the TreeSet, as far as I recall, it's a balanced search tree. Okay, so you will see it's a little bit more than what we implemented, but starting from what we implemented, basically you have the foundation of also what is behind these collections that Java offers you in the Java util package. No, you certainly heard about the TreeSet, and if you didn't hear, then I do advise you to review the Java Fundamental series as a refresher, because they are important implementations in the Java Collections framework. Okay, with that being said, I don't want to keep you more than that. I wanted to cover this essential data structure, and then of course next lessons I will complicate it. I will complicate it, and I will explain more about different kinds of trees, including heaps and other implementations, that are other structures that I find to be essential. With that being said, thank you very much again. I'm waving goodbye. Have an excellent time for study further, and hope you enjoyed the lesson. Cheers.